In this video, we are going to look at calculus with parametric equations, and we're really going to focus on integration here. So let's look at how do we find the area of a parametric curve. Let's say we have a curve that's non-intersecting, which means it doesn't cross itself, defined by the parametric equations x equals x of t and y equals y of t on the interval from a to b inclusive. Assume that x is differentiable, and if we want to find the area under this curve, the area is equal to the integral from a to b of y of t times x prime of t, the absolute value of that, times dt. So if we look at this example 4 equation, we're looking at a cycloid. We have x of t equals t minus sine of t. Y of t is 1 minus cosine of t. And we're looking at the interval from 0 to 2 pi. So I'm going to graph this in Desmos. And you can see that cycloid coming out of that kind of looks like a half of an ellipse, if you will. We're going to try to find that area. So the absolute value of that is going to give us a positive that's coming out. So we're thinking about this being in above the y-axis. So let's take a few derivatives. If I take the derivative of x of t, the derivative of t is 1. The derivative of minus sine would give us a minus cosine of t. And then to find our area, it's going to be the integral from a to b, absolute value of y of t times x prime of t dt. So we're integrating from 0 to 2 pi. Those are my bounds, a to b. Absolute value. Y of t is 1 minus cosine of t. X prime was 1 minus cosine of t. And then dt. I must simplify what's going on here. When I multiply 1 minus cosine t times 1 minus cosine t, I'm going to get 1 minus 2 cosine of t plus cosine squared of t dt. I'm going to graph that to see what I need to do with that absolute value. See if that already lives above the x-axis. 1 minus 2 cosine t plus cosine squared of t. Let's change this to x. It's not liking what I'm typing in. There we go. We see that does live above the x-axis, so we could drop the absolute value at this point. One minus cosine of t plus cosine squared of t dt. So I can integrate the 1 and the cosine of t, but I'm going to have to do a substitution for the cosine squared. I know cosine squared using power reduction formula is 1 plus cosine of 2t over 2. So let's write that. 1 plus cosine of 2t over 2 dt. I'm going to simplify this before I do anything else. So this is going to be 1/2 plus cosine of 2t over 2. And 1/2 plus that 1 is going to give me a 3/2 there. So we have 3/2 minus cosine of t plus cosine of 2t over 2. And I'm going to write that as 1/2 cosine of 2t. So when I integrate this, I need to think about integrating each piece separately. The first two I don't need to do anything special to, but that last one requires a u substitution, and that u substitution only would be needed for that last piece. So I'm going to split these integrals up I can keep the first two together since they're just basic, but I'm going to pull the 1/2 out and then integrate that last one separately. So when I integrate 3/2, I'm going to have 3/2 t. When I integrate cosine, I get positive sine, and positive times that negative would give me a negative. To integrate the cosine of 2t, I need a 2, and I need to compensate with a 1/2. That way I'm multiplying by a well-chosen 1. And when I integrate cosine of u, I'm going to get sine of u, and my u is 2t. And then we're going to evaluate this from 0 to 2 pi. Oh, let me correct something. That middle term was a -2 cosine of t, and it looks like I dropped my -2. So I'm going to go in and fix that. So we're really integrating 3/2 minus 2 cosine of t plus 1/2 cosine of t. We can integrate the first two terms by themselves. My final integral would be 3/2 t minus 2 sine t minus 1/4 sine of 2t. Now I need to evaluate from 0 to 2 pi. So when I plug in 2 pi, and then I'm going to plug in 0, and we know the sine of 2 pi is 0, and the sine of 4 pi is 0, and the sine of 0 is 0, and 3/2 times 0 is 0. So that's going to leave me with 3/2 times 2 pi, which is going to be 3 pi. So that would be the area under the curve there. So let's talk about arc length. Consider the plane curve defined by the parametric equations x equals x of t and y equals y of t for t bounded between t sub 1 and t sub 2. And we're going to assume x and y are differentiable functions. The arc length of this curve is going to be the integral from t sub 1 to t sub 2 of the square root of dx over dt squared plus dy over dt squared dt. So when we think about arc length, what's happening is we're taking our arc, whatever that function is, on some interval, and we're thinking about the change in x and the change in y, and we're really dividing it into tiny, tiny, tiny little triangles, and I can look at that change in x and that change in y, and then if I were to add up all the hypotenuses for all of those triangles, then I would get what that arc length is. But since I have an infinite number of those triangles, and that's where the integration is going to come from. So this is actually coming from that Pythagorean theorem. So let's look at an example. We want to find the arc length of the semicircle defined by the equations x of t equals 3 cosine of t, y of t equals 3 sine of t. And we're only looking from 0 to pi. So let's find our x prime of t and our y prime of t. The derivative of 3 cosine would be -3 sine, and the derivative of 3 sine would be 3 cosine. So arc length, and they're using the lowercase s for arc length. For this set of parametric equations from 0 to pi would be the square root of x prime of t, which is -3 sine of t squared, plus y of t, which is 3 cosine of t squared dt. So this is going to be non-sine squared of t plus non-cosine squared of t dt. And I'm going to factor out a 9, and that's going to leave me with sine squared plus cosine squared. And we know sine squared plus cosine squared is equal to 1. So this is really 9 times 1 under the radical, which is 9. So if I take the square root of 9, I'm going to get 3. And then now I'm in a place where I can integrate. So when I integrate 3, I'm going to get 3t, and I'm evaluating from 0 to 3. So this is going to be 3 times. Oh, give me just a second. I accidentally changed my bounds. They're going from 0 to pi, not 0 to 3. Oh, I wrote it again. Try again. There we go. So then we're going to have 3 times pi minus 3 times 0, which is 3 pi. So that would be the arc length for this parameter, for this parameterized curve between 0 and pi. So we can expand on this to find surface area. Of a curve that's written parametric, surface area would be equal to 2 pi integrating from a to b of y of t times the square root of x prime of t quantity squared plus y prime of t quantity squared. So let's look at an example for that. We've got x of t is defined as t cubed, y of t is equal to t squared, and we're bounding t between 0 and 1. And if I want to find surface area, and I'm going to use that capital cursive S, it's going to be 2 pi times the integral from 0 to 1, y of t, which is equal to t squared, and then the square root of x prime of t. My x prime of t here would be 3t squared, and I'm squaring that, plus y prime squared. Y prime is 2t. I'm going to square that dt. So we're going to get 2 pi integral from 0 to t. This is t squared square root of non-t to the 4th plus 4t squared dt. So let's see if we can integrate this. We could factor a t squared out, and that's going to leave us with non-t squared plus 4 dt. And the square root of t squared would be t. And t times that t squared outside would be t cubed. So I have t cubed times square root of non-t squared plus 4 dt. So I think we could integrate this with a trig sub. Let's try it. If we remember back to the trig sub section, we've got u squared plus a squared under the radical. And we're going to use u equals a tangent of theta. So that means u over a is equal to the tangent of theta. So in this case, we're looking at non-t squared, which is 3t squared, quantity squared, plus 2 squared. So my u is 3t, and that's going to be equal to a, which is 2 tangent of t. Sorry, tangent of theta. So 3t over 2 is equal to the tangent of theta. I can draw a triangle based on that. Tangent is opposite over adjacent. So this side, Pythagorean theorem would give us, so we have 2 squared plus 3t quantity squared is equal to that hypotenuse squared. And that would be the square root of 4 plus non-t squared. We know tangents and secants go together. So the secant of this triangle would be equal to 1 over cosine. Cosine is adjacent over hypotenuse, so that would be hypotenuse over adjacent. And I think we have enough information to make some substitutions here. So the square root of 4 plus 9t squared would be equal to 2 secant of t. Secant of theta. So I can substitute this for 2 secant of theta. And that t cubed is going to come from this. So let me draw a line here. How do I solve that for t? I'm going to multiply everything by 2/3. So I'm going to have 2/3 tangent of theta, and that's going to be cubed because it's t cubed. And then the derivative of t, the derivative of tangent is secant squared. We took that derivative with respect to theta. So I made a substitution for the t and cubed it. I made a substitution for that square root, and now I'm making a substitution for dt. And then we're going to have to think about those bounds. Let me clean this mess up first. So I have 2 cubed over 3 cubed. That's going to be 8 over 27 times 2 over 3, which is going to be 16 over 27 times 3 is 81. And that's going to be times a 2, which is 32. So this is tangent cubed, secant cubed. So I'm going to move this number outside. 2 times 32 is going to give me a 64 pi over 81, and I'm integrating tangent cubed times secant cubed. I'm going to think about this as tangent squared times tangent. I'm having a hard time with my computer. Bear with me a minute. Tangent squared times tangent. And then I can do a substitution for that tangent squared there. So my goal is to write things in terms of secant. So the secant's my u, and the derivative of the secant is the secant tangent. So tangent squared is equal to secant squared minus 1. And I'm going to multiply that by tangent secant. Let me write it this way. Well, let me go ahead and do that, and then I'll show you what I'm thinking in my head. Okay, so there's what I got. So here's what I'm thinking in my head. I'm thinking I'm going to reserve a tangent and a secant so that when I distribute, I'm thinking about u being secant of theta. And then the derivative of the secant is secant tangent. So we're going to have secant to the 5th of theta times tangent of theta minus secant cubed of theta times tangent of theta, d theta. So I'm going to have secant to the 4th of theta times secant theta, tangent theta, minus secant squared theta times secant tangent. So if u is secant, derivative of the secant tangent, u to the 4th becomes u to the 5th over 5. And then u squared becomes u cubed over 3. And then we're going to make some substitutions back. Notice I left the bounds off when I converted because my goal, I'm going to go back to t so I can plug in the 0 and the 1. So I've got 64 pi over 81. And I'm going to have 1/5 times secant to the 5th minus 1/3 times secant to the 3rd, going from 0 to 1. Secant, we said, was the square root of 4 plus 9t squared over 2. So I had to pause the video on the last one, and I decided to go ahead and complete this problem. So we were right here where I had rewritten our trig integral solution back in terms of t's by using our substitution for secant. Secant is equal to square root of 4 plus 9t squared all over 2. So I substituted that in for the secant. So I've got 1/5 times that substitution to the 5th minus 1/3 times that substitution to the 3rd. And so from there, I went ahead and wrote everything out. This is going to give me that final answer for that definite integral. So I'm going to plug in the 1. When I plug 1 into for t under the radical, it's going to be a 13. So I'm going to have 1/5 times the square root of 13 over 2 raised to the 5th minus 1/3 times the square root of 13 over 2 square root of 13 divided by 2 raised to the 3rd. And then when I plug in the 0, so 0 is going to go in for the t here. So I'm going to have the square root of 4 plus 0, which is just the square root of 4. So I'm going to have 1/5 times the square root of 4 over 2. That's going to be raised to the 5th minus 1/3 times square root of 4 over 2 raised to the 3rd. But notice the square root over 4. The square root of 4 is 2, and 2 over 2 is going to be 1. So this is going to reduce to 1/5 times 1 minus 1/3 times 1, which is where this is coming from. And then if I were to multiply some things out, I'm going to have that square root of 13 raised to the 5th, or I can think about it as 5/2. And then that 2 is going to be raised to the 5th. So that's going to be 32. And 32 times 5 is going to give me a 1/60 for that denominator. That second fraction, I'm going to have 13, square root of 13 cubed is 13 to the 3/2 over 2 cubed, which is 8, times 3, which is 24. And then when I simplify 1/5 minus 1/3, that's a negative 2/15. So minus negative 2/15 gives me a positive 2/15. So my final answer is 64 pi over 81 times 13 to the 5/2 over 160 minus 13 to the 3/2 over 224 plus 2 over 15. And if I were to get a decimal representation for that, it's about 4.9364. And I can check that using something like Wolfram Alpha. And if I were to type this in, it will give me the same decimal representation.